Hi students. So today I'm going to take periodic classification and properties chapter. Here it is small chapter and very important. It gives lot of information. Periodic classification and properties. First part is like a classification of elements. The different scientists tried different ways to classify the elements. That for every scientist they had some drawback. So merits and demerits, everything we will discuss. And one more thing, my question is why we need to classify these elements? Why we need to classify these elements? First, I'll put heading. Need to classify the elements. Reason is just to know the properties. To know the properties. Something. In simpler way, we can find study the properties of elements if we divide them into similar groups and groups. So here how they made classification. Similar elements occupies means they arranged in vertical and those are called groups. So element belongs to same vertical line or column. They have same properties. Such with the arrangement. Suppose first group elements, if you see lithium, sodium, potassium, rubidium, generally they chemical properties most of the cases one element property resemble with another element property. Since they have same values electronic configuration. In that way, we can study the properties of elements in less time and easier way we can. That is the reason they classify the elements. To study the properties of elements in easier way. Classify the elements. So here earlier attempts if we see periodic classification. What is the answer for this? To study the properties of elements in easier way. Properties of elements. Easier way. Now, earlier attempts of classification. First one, Dobereiner triads. Dobereiner. So according to Dobereiner triads, average of if we arrange elements with increasing order of the atomic weights, average atomic mass of first and third Average of atomic masses of first and third elements is equal to or approximately equal to the atomic mass of second element or middle element. If we arrange elements with increasing order of atomic weights, what is the condition, friends? To arrange elements in increasing order of atomic weights. Increasing order of atomic masses comma average of atomic masses of third element is equal to or approximately equal to atomic mass of element or middle element. Middle element. Example for this. If I give example, you can understand better. Lithium, sodium, potassium. If you take lithium atomic mass 7, potassium atomic mass 39. Average of these two, 7 plus 39 by how many elements? 2 elements. 1%. So here it is equal to 46 by 2, which is equal to 23, is equal to the atomic mass of sodium, middle element. So these three elements are satisfying the condition, the Dobereiner triad concept. So these three elements are having same properties. So we can arrange these three elements in the same. Same thing if you see calcium, strontium and barium. One more triad is calcium, strontium and barium. Calcium atomic mass is 40, strontium and barium. So here barium atomic mass is 137. So average of these two, 40 plus 137. How much? 177. Around 88 will get 88.5 like that you will get. So which is equal to average atomic mass of the strontium atomic mass is 88, approximately equal to, here we will get 88.5. Next, so here you no need to remember all the atomic masses and average, you no need to do. How they are asking question, students? You need to identify which is Dobereiner triad. Among the following, which represents the Dobereiner triad. Reason is, all the elements in the periodic table are not following this concept. This has some limitation. Only some elements he could arrange in triad form, not every element, not all the elements. So this theory has limitation. So only few elements. So they may ask question like this. Not they may, they are asking like this. Among the following, which represents Dobereiner triad. So even you can take beryllium, magnesium, calcium also. Chlorine, bromine. These are the important examples of Dobereiner triad. Next classification, here I told demerit. He could arrange few elements in not all the elements. Not all the elements. Next one, Newlands law of octave. Newlands law of octave. According to Newlands, same atomic weights only had taken reference. According to Newlands, if we arrange elements with increasing order of atomic weights, every eighth element shows the properties of first element. That means repetition of the properties of elements occur at every eighth element. So it is called octave rule. So example, if you see lithium, beryllium, boron, carbon, nitrogen, oxygen, chlorine, 1, 2, 3, 4, 5, 6, 7, 8 elements. That time nobody has not discovered. Magnesium, calcium. Afterwards, and this theory also applicable till calcium, not beyond calcium. After that, scandium and all will get. So this theory is applicable till this law is applicable till calcium. Newlands octave. And the elements are arranged in order of increasing atomic mass. So every eighth element has the property similar to those of the first element. So repetition of properties occurs after every eighth element. every eighth element property of element or shows the liquidity. Every eighth element resembles the properties of first element. So it is Newlands octave rule. Okay, students. Next one, demerits. This law is applicable till calcium. Beyond calcium, it's not applicable. Not applicable. This is the main drawback in this. Next one, Mendeleev's periodic table. Mendeleev's periodic table. What is Mendeleev's periodic table? Periodic law. What is Mendeleev's periodic? So Dobereiner also used atomic weight concept only in triad form. In triad form, how you know? First average of with increasing order of atomic masses, if we arrange these elements, every first and third element, average of atomic mass of every first and third element is equal to the atomic mass of second element or middle element. Sorry, proper way. When the elements are arranged with increasing order of atomic weights, average of atomic mass of first and third element is equal to the atomic mass of middle element or second element. Next one, there are some drawbacks. I told you know only few elements he could arrange in triad form, not all elements. And octave rule, he also he had taken even atomic weight as reference, and he arranged all the elements with increasing order of atomic weights, and he observed every eighth element shows the property or has the properties of first element, but only certain extent, not more than that. Till calcium only we can observe. Afterwards, the properties will not be repeated. So that was the drawback. Then Mendeleev started. Mendeleev also had taken atomic weight only reference. According to Mendeleev, physical and chemical properties of the elements are the periodic functions of their atomic masses or atomic weights. Physical and chemical properties of the elements are the periodic functions of their atomic weights. Even definition is also important for the board economics. I'll write here. Physical periodic function for atomic weights. This is Mendeleev's law. Mendeleev's periodic law. Even he has some merits and demerits also. Some merits also. In his periodic table, total 63 elements. He could arrange 63 elements in periods and groups. So total 63 elements are present in his periodic table. And sometimes they are asking how many periods, how many groups are present in Mendeleev periodic. This table consists of 7 periods and 8 groups mainly. So what he did, in that EAB division he did in groups 1A, 2B, or 1B, 2A, 2B, like that division here. And so main groups are 8 only. 7 periods and 8 groups. There are 7 periods and 8 groups. Next, merits, if we see, merits. He left space for unknown elements. Means he predicted existence of elements, some elements. So he left space for unknown elements. There are some elements which we have to discover. Unknown elements. Example, if we see, given some names of, he predicted some element existence and he gave the name boron, aluminium, gallium. So boron, present it is scandium. Important stone. Silicon, germanium. Boron, aluminium, gallium. So they boron, aluminium. Now they may ask, boron, scandium, aluminium. So one mistake I did. Wait, sorry. Boron, aluminium. Aluminium is gallium. Silicon. Because silicon is germanium. Boron, scandium, aluminium, gallium, silicon, germanium. These are the unknown elements, and here given the names like boron, aluminium, silicon. Present scandium, gallium, and germanium. And he corrected a few elements atomic masses also. One more merit was beryllium atomic mass from 13.5 to 9 he corrected. He corrected atomic mass of beryllium from 13.5 to 9. Actually, equivalent weight into valency is nothing but atomic weight, right? So, equivalent weight is 4.5. Earlier, they considered it in 13th group, so valence they have taken 3, 13.5. Later, he adjusted it's 4.5. Consider it is second group, resemblance with second group, and he corrected atomic mass of beryllium is 9 gram. 9 gram was under 9. Next one, demerits. Demerits. So here, if we follow strictly atomic weights, increasing order of atomic weights concept, some elements properties are not visible. Then he thought that there might be some atomic weight measurement problem, not here. So what he did, with respect to the properties only he arranged similar groups, not according to weight in some cases. So some heavier elements occupied first, some lighter elements occupied next. Means increasing atomic weights concept he couldn't follow strictly. If we follow, the elements properties are not same, means their properties will become different. So he thought some atomic weights measurement mistake might be there. So he followed properties only, not atomic weights strictly. So some heavier elements occupied first, lighter elements occupied next. That is one problem. Some heavier elements like argon occupied first, then potassium. Argon's atomic mass 39.9 around. Potassium atomic mass 39.1 around. So heavier argon atomic mass is more than potassium, still it occupies first. So that in that cases he couldn't follow atomic weight. Heavier elements next. Second drawback, no position for isotopes. Means no separate position for isotopes. Example, if you take hydrogen has three isotopes, one H1, one H2, one H3. We follow atomic weights concept. Three positions we have to give. Three positions, not even one particular position for hydrogen. Hydrogen position not a fixed. It is in air. Since hydrogen behavior, it is behaving really. Really means it behaving like first group elements and some properties are eliminated with the 17 group elements. It can lose electron like the first group elements. It can gain one electron like 17 group elements. So hydrogen position not at fixed. Specific position for hydrogen. These are the main drawbacks of Mendeleev's periodic table. Next one, modern periodic law. Modern periodic. So whoever selected atomic weight as reference, they all got drawbacks like isotope position, increasing atomic masses, all the elements couldn't arrange in a particular sequence. So then Bohr, Mosley, all those people again they try to overcome those drawbacks and they realized that no two different elements are having same atomic number. So it is better to take atomic number as reference, not atomic weight. So in modern periodic law, they introduced atomic number. Means they have taken atomic number as reference. Same Mendeleev's law is modern periodic law. They are asking in exam maybe. You can write same as Mendeleev's law only, but last atomic weight you just replace with atomic number. Only so much. Physical and chemical properties of the elements are the periodic functions of their atomic number. Atomic number. Periodic functions of the atomic number. So like this, they arranged known elements in 7 periods. And 18 groups. So these horizontal rows are there, no? Those are called groups, sorry, periods. Vertical column. So like this, known elements they arranged 7 periods and 18 groups. They arranged in. So modern periodic table contains 7 periods and 18 groups. So in that, we'll see about periods. First period, it contains only two elements. So it is called shortest period. Hydrogen and helium only. Shortest period. Second and third period, if you take, they have 8 elements. So they are short periods. Shortest, short. Next, fourth and fifth. They have 18 elements, so they are called long periods. Sixth and seventh, especially the sixth one, and so 32 elements, so it is called longest period. Seventh period, they are considered incomplete period. Now it is filled. There's almost that left, whatever the space left by Mendeleev is almost in seventh period, but incomplete right now. Incomplete. This also longest one. Okay. Based on the number of elements, first period is called shortest period, second and third periods are called short period, fourth and fifth are called long period, sixth and seventh are called longest periods. Next, what about groups? Groups. First group elements. Like we said, group and name. Okay, first group. Group 1, alkali metals. Alkali means, students, base which is soluble. Base which is soluble. So alkali metal bases are bases formed by alkali metals are soluble in water. Formed by alkali metals are soluble in water. So these are called alkali metals. Next, second group elements, alkaline earth metals. Third one, 13th one, Why we call alkaline earth metals? Even these elements bases also are also soluble in water. They are basic and are soluble in water, and the abundance on earth crust is also alkaline earth metals. Next one, 13 group elements, boron, aluminum. Here that group starts with boron, so these elements are called boron. The group is called boron family. 14th, carbon. Carbon is the first element, parent element. 15th group, nitrogen. Nitrogen को फिर भी कर. Then means suffocation. When we inhale these elements compounds, 15 group element compound formed by 15 group elements will get suffocation. Example, ammonia is it. If you inhale more, get breathing problem. If the concentration, if it is more, sometimes it leads to death also. So it is very, very dangerous. Inhaling ammonia in large quantities or concentrated. So cold and all sometimes they use, but little quantity is okay. More nitrogens. Next one, 16th group. 16th group. Chalcogens. Chalcogens means ore forming elements or ore generators. Ore forming. Here, ore forming means most of the ores available in the form of oxide, sulfide. Oxide, sulfide. So, these are also called ore forming elements. Iron oxide, mercury oxide, zinc oxide. These are all the ores. Aluminum oxide, that is also ore only. So, these elements combination is there in the ore composition. So, ore forming elements, chalcogens. 17th group, halogen. Salt generators. Halogens are. What is the halogen mean? Salt generators. 18th group, noble gases, since they don't react with other elements. Inert gases, the chemical reactivity is very less. Inert gases. Inert gases, all these elements are gases only. They have stable electronic configuration, that is the reason they are not involved in chemical reaction except the few. These elements are also called zero group elements. Zero group elements. The valencies are zero. Valency of these elements is equal to 0. Next, another classification. Representative elements. Representative elements. See students, groups S and P, SNP, I have not introduced that classification, so I'll use another word. Groups 1 to 13 to 17th group. 17. Elements of the groups, better to use. Element belongs to first group, second group, 13th to 17th are called representative elements. Why these are called representative elements? Why 18th group is not included in this classification? Representative elements. 18th group elements, they all have sufficient number of valence electrons. They have stable electronic configuration. Other elements are trying to follow such electronic configuration, try to acquire such type of electronic configuration, octet or duplet configuration. They try to get nearest noble gas configuration. So suppose if chlorine is there, it try to get neon configuration. Sodium is there. Sodium atomic number 11, neon atomic number 10. By losing one electron, it try to acquire neon configuration. Chlorine is there. Chlorine try to acquire argon configuration because for chlorine, argon is the nearest noble gas. So like that, these 1 to 17 group elements, they try to acquire stable configuration like noble gas. So these are called representative elements. Next one, transition elements. Transition elements. Groups. These are now important. Groups 3 to 11. 3 to 11 are called transition elements. Why 12th group is not included? Otherwise, all D block elements. I'll explain what is D block element. What are the D block elements? All D block elements except 12th group. Are called transition elements. 3 to 12. Groups 3 to 12 are come under D block elements. But 3 to 11 come under transition elements. From this, what we can say, all transition elements are D block elements, but all D block elements are not transition elements. Why? In D block elements, 12th group elements are not come under transition elements. What are the 12th group elements? Why they are not come under transition elements? We'll see now by taking those examples. Example of 12th group elements: zinc, cadmium, mercury. Zinc atomic number 38, here 48 plus 32, 80. Mercury 80. So here if you write electronic configuration, argon 4s2 3d10. Up to argon 18 electrons will cover 4s2 20 10. Next, if you write cadmium, argon after argon, krypton will come 5s2 4d10. Next will be 6s to 5d10. What did you observe, students, in this? Both S maximum capacity of electron, S subshell maximum capacity of electrons 2, D subshell maximum capacity of electrons 10. Okay, so S has reached its maximum capacity, D has reached its maximum capacity. Yes, both S and D completely filled, and these elements are having stable configuration, and also DD here transitions are not possible, isn't it, students? D is completely filled, S is completely filled. So promotion of electron or transition from one orbital to another orbital of shell is not possible. So transitions are not possible. It is like in the class 20 benches are there, 20 chairs are there, all 20 chairs occupied by 20 students. First, this is the first case. Second case, 20 chairs are there, 10 students are there. They can choose the chair. They can go from here to there, there to here. First case, exchange may possible, but transition may not possible. Okay. So DD transitions are not possible. So here transitions are not only DD, transitions are not possible. So in 12 group elements do not come under transition elements. Understood, students? Representative elements S and P except 18 group. Otherwise group 1, 2 and 13 to 17 except the last group. Here also D block elements also last group, 12 group will not come under. Most of the people still they get confused. What is the difference between transition elements and D block elements? 3 to 11 groups come under transition element, 12th group does not come under transition element. So group 3 to 12 are called D block elements, 3 to 11 are called transition. Most of the transition elements are paramagnetic. That magnetic properties and all we can discuss in other inorganic chemistry. Next. Next is inner transition element. Inner transition elements. Inner transition elements. In periodic table down at bottom there are 2 rows with 14 elements. Those are called inner transition elements. Inner transition elements. It belongs to third group. It belongs to third group. And periods if you see 6 and 7. These elements belong to all inner transition elements belongs to third group. They may ask this question. Belongs to third group. Belongs to third group. 6th and 7th period. Landmass action and cycle. So bottom of the periodic table there are 2 rows, 14 elements. These elements are also called F block elements because last electron enters into F subshell. In the transition elements belongs to third. What are those elements? Helium to lutetium, helium to lutetium, thorium to larynx. law, neutron element. Next one, classification of elements into blocks. S, P, D, blocks. First heading, S block elements. S block elements. And what are which and all groups come under S block elements? Here, S block elements, last electron or differentiating electron, if it enters into S subshell, then those elements are called S block elements. Example, if you see lithium, differentiating electron enters into S subshell or last electron. Elements in which last electron enters into S subshell. Example, if you take lithium, atomic number 3, 1s2, 2s1. Here last electron is in S subshell. The same way, magnesium, if you take 1s2, 2s2, 2p6, 3s. Here also last electron is in S subshell. So these are S block elements. So in group 1 and 2, alkali metals, alkaline earth metals, both cases alkaline earth metals. Come under S block. Alkali metals and alkaline earth metals, last electron enters into S subshell, so they are called S block. They are come under S block elements. If they see general valence electronic configuration of these elements, NS122, NS122. So here N is valence shell number. Valence shell number. So all these elements are metals. All S block elements are metals. Next one, P block elements. P block elements. Here, groups from 13 to 18 except helium. From 13 to 18 come under P block elements. 13 to 18 come under P block element. Since last electron enters into P subshell. Example, 13th group element, first element is boron. First one is boron. Boron atomic number how much? 5. 1s2, 2s2, 1s2, 2s2, 2p1. Last electron is in p subshell. The same way, carbon if you take first element in the 14 group, 1s2 atomic number 6, right? 2s2. All these elements, last electron enters into p subshell. What is the general valence electronic configuration? Sometimes there are ns2 here will be figured. np 1 to 6. Since p subshell maximum capacity of electron 6. ns2 np. This block consists of metals, non-metals, and metalloids also. So this block consists of non-metals more, metals few, even metalloids also few. S block elements only metals. P block elements consists of non-metals, metals, all types of elements are there. Next, D block elements. D block elements. So here already it is there. Groups. Last electron enters into p subshell. Here last electron enters into differentiating electron enters into D subshell. Differentiating electron enters into D subshell. Which and all groups come under D block elements for 2, 3 to 12. And what is the general valence electronic configuration? Ns 1 to 2, n minus 1, D 1 to 10. Even sometimes 0 also possible. 0, 1 to 10. Okay. This is the general valence electronic configuration of transition. Even these elements more are also metals. All are metals. This block is present at the middle. S block elements extreme left to the periodic table. P block element extreme right to the periodic table. D block in between S and P. F block elements present at the bottom of the periodic table. F block elements already discussed in the transition. This is about classification of elements into blocks. Next, by knowing electronic configuration, how to find out group number, period number. prediction of with the electronic configuration. Otherwise, the heading don't want it, like one simple concept. How to find out group number and period number by using electronic configuration. See students, period number is equal to valency shell number. Group number valence, but it differs from block to block, right? Valency electrons or valence electrons. In case of S block elements, S and P block also, you can apply direct concept, above concept directly. Above concept you can use directly. Suppose you are given with one element, that is potassium, atomic number 19. Electronic configuration is argon 4s1. So this is the last shell, isn't it? So potassium belongs to valence shell is 4, right? So the period number is equal to 4. 4. And the number of valence electrons, how many are there? How many electrons are there here? Only 1. So that itself group number. So potassium belongs to first group and 4th period. Like this. Magnesium hydride. Atomic number 12. What we have to take nearest noble gas neon? 3s. 3s. So third shell is the last shell. So period number is 3 and number of valence electrons in that. So magnesium belongs to group number 2 and period number. Understood students? Be like this, you can find out. Suppose here boron, atomic number 5. Helium, 2 electrons will be covered. 2s2, 2p1. Here group number 3 you don't write students. 10 plus 3. If element belongs to P block, 10 plus 3, because 10 groups are there. D block is there in the middle. Here there 10 groups are there. No? So 10 you have to add. 10 plus 3. So here group number, if the period number is same, no need to change anything. Period number is 2. Group number we have to add 10 plus 3. 10 plus 3. In P block elements you have to do that. So 13 group. Understood, right? Next, suppose in neon, if you take neon atomic number 10, helium, then also you can write 2s2, 2p6. So last, how many valence electrons are there? Group number, period number will not change. So only group number 10 plus 8. Valence electrons 8, right? 18. This is modern notation. Next, You go for D block elements, it's still different. D block elements. D block elements. In case of D block elements, period number is as is. But group number, while considering group number, ns electrons and sum of the ns and n minus 1 into d electrons. Here also example is okay. Chromium, atomic number 24. Electronic configuration argon 4s2. Actual abnormal electronic configuration 4s1 3d5. 4s1 3d5. Here last shell is 4, not 3, because 4 will come after 3 only. No? Fourth shell. So period number is same. 4. Group number, what did I say? S and D, ns, n minus 1. Outermost shell and inner d electron. Group number is 6. So chromium belongs to 6th group, 4th period. Zinc will see. Atomic number 30. Argon 4s2 3d10. 4s2 3d10. So here period number is 2. Group number is ns and n minus 1. So, like this, we can find out group number, period number in case of S, T, and D. For F block, already I told they belong to 3rd group and 6th and 7th. Lanthanide belongs to 6th period, actinide belongs to 7th. Next, heading periodicity and periodic properties. First of all, what is periodicity? Periodicity. Recurring of the properties of elements after certain intervals. Recurring of the properties of elements after certain intervals. That intervals are there. Is that Newlands is said, but they prove it is wrong. Then those intervals in the form after 2, 8, 18, 18, 32. After these intervals, so these regular intervals, properties of elements repeats. Because elements will get similar valence electronic configuration. What is the cause of periodicity? Also we lost. Cause of periodicity. What is the cause? After certain intervals, valence electronic configuration repeats. Those elements are having same valence electronic configuration, so they exhibit same properties. That is called periodicity. So those intervals are 2, 8, 8, 18, 18, 32. After these regular intervals, properties of elements repeat in electronic configuration. The periodicity, cause of periodicity is due to this elements will get same valence electronic configuration. Same valence electronic configuration. Now, periodic properties, if we see, there are some periodic properties, they change from group to group, period to period. Those are atomic radius or ionic radius, ionization energy or ionization enthalpy, electron affinity or electron gain enthalpy, electropositivity, electronegativity, even valency also. Valency also will change. It's a trend. First it increases and then decreases. So that is the way. Okay, periodicity. Now, periodic properties, if you see, first five heading, atomic radius. Atomic radius. What is atomic radius? If this is atomic atom, is a nucleus, from here to the last shell, where the electrons are present, itself radius. Since atom we are considering a circular shape, the radius will be like this. Is the distance between center of the nucleus to the outermost shell. Okay, right now. Distance between the center of the nucleus to the outermost shell. Outermost shell where the electrons are present. The atomic radius. So, variation of atomic radius and the